In a previous lecture, we had introduced the relationship between voltage and the electric field. We said that voltage, or really the difference in voltage, is going to be integral of minus E dot ds. Now, it's important to know it's not just voltage, it's difference in voltage. Because voltage, remember, is electrical potential energy over Q, the electric potential, as we call this. Voltage and electric potential are synonymous terms. And so there's no real zero of electric potential. Just like there's really no zero of gravitational potential. When you're talking about, for example, a pendulum, then you could define the zero to be the bottom, or you can define the zero to be here, or the zero right here. You know, potential energy is kind of a relative. What really matters is the difference in potential energy between there, and that is how you figure out how fast it's moving at the bottom. You would say that the mgh is 1/2 mv squared. So that's how you do it. Okay, but it doesn't really matter whether you define that to be zero or define this to be zero. Either way, it's going to be the same, because the only thing that really matters is the height right there. Likewise, in electrical potential energy, there's not really a zero. You can define a zero to be someplace convenient, but that all that really matters is the difference. Because you imagine you have power lines, and these power lines can be very high voltage. And so you got these power lines, you know, like above ground power lines here, and you got a squirrel running along the power lines. And so this might be, you know, a 10,000 volt power line. Well, these are not insulated wires, they're bare wires. So the front end of the squirrel is 10,000 volts. The back end of the squirrel is 10,000 volts, so the difference is zero. And there's no problem, because you have a difference of zero right there. The problem is the pole is at 0 volts. And so to avoid, you know, electrical discharge here, we have little insulators that hold the wires up. Now, if the squirrel is down here and decides to step out and make a contact between something at 0 volts and the back end of the squirrel is 10,000 volts. So the difference in voltage is 10,000 volts. Now current goes through here, dead fried squirrel falls down to the ground, and then what happens is everybody's electricity has a little glitch in it. And so again, the same sort of thing would happen with your car. As you drive your car down the road, you got a battery in here providing, you know, power to the electrical system of the car. Really, it's the alternator is doing that. But you normally say that it's a 12 volt system. Now, really, if the alternator is working right, it's really a couple volts more than that, but we'll say 12 volt system. But as the car is driving down the road, what happens is that the car can actually pick up a voltage relative to the ground. So the ground is 0 volts. The car might be a kilovolt. Well, that means that the wires inside the car are going to be 1,012 volts. So the difference in voltage between the wires and the frame of the car is 12 volts. Okay, so once again, what matters is this difference, not the actual voltage itself. Okay, we'll talk more about this later, even when we get into electrical current, electrical systems, because again, you find a similar sort of issue when you're talking about wiring in the house and the voltage differentials that are there. Okay, so now what we're going to do here, though, is remember that the voltage is integral E dot ds if minus integral E dot ds, and so what we find is that we had previously said that the electric field you can get as minus the gradient of the voltage. Okay, and I explained that before as well. And so that means you take the derivative with respect to x in the x direction, derivative with respect to y in the y direction. Well, this turns out to be an interesting sort of thing, because if you imagine an electric field like that, and you're going along the electric field in that way, you're going with the electric field, so you are decreasing voltage. If you go this way against the electric field, you are increasing voltage. What if you go perpendicular to the electric field? Well, the difference in voltage is minus integral E dot ds. If my ds is perpendicular to the field, the dot product is 0, and so along that path right there, then the change in voltage is 0. So that means that along this line right there, that you can move back and forth along that line without changing voltage. Well, if the electric field also extends, behind the screen and in front of the screen, then you have a plane or a surface of constant voltage. In fact, if the electric field is curved like that, you can draw a surface that is always perpendicular to the electric field, and if you move along that surface, then the change of voltage is 0. We call that an equipotential surface. So, if you move along an equipotential, you are moving perpendicular to the field lines. In fact, this is actually one way that you actually measure fields, because it's very difficult to actually directly measure the fields. So what you will sometimes do is you could actually measure the electric potential, use a voltmeter or something to measure electric potential difference between 2 points, and so you can trace out where the potential difference is 0, and that means that you've found this equipotential surface. If you know the equipotential surface, then you know the direction the fields are going. For example, if I were to figure out that my equipotentials are like this, so that's going to be 1 volt, 2 volts, 3 volts, 4 volts, and then I say, what does the field look like? Well, the field lines have to always be going perpendicular to the potential. So the field lines are going to be looking like that. If my equipotential look like that, and I want to know where's the field doing, so if this is 1 volt, 2 volt, 3 volt, 4 volt, I would know that the field lines are doing something like that. So the electric field would have to always be going perpendicular to those equipotentials. And so this is one useful strategy here in terms of figuring out the relationship between voltage and electric field. And again, this gets back to the idea that the electric field is minus the gradient of the voltage, or the difference in voltage is minus integral E dot ds. Okay. And those concepts give rise to equipotentials and what we were just talking about. This also explains both sections 3 and section 6 in chapter 24.